Okay, guys, welcome to the second lecture on reinforcement learning. Um, let's get started. So, okay, so just to recap. So last time, I gave a little story about how we can how we calculate averages and expected returns, and we use the the K-arm bandit as a sort of test bed to sort of drive that. And we ended with this scenario where now the bandits are changing every time. So now you have to use the context, some kind of other features. Use your current use this current state to determine what action you should take at this point, right? When I have the green bandit, I should pull the third arm. When I have the red bandit, I should pull the second arm. And so we introduced this concept of a policy, right? That the policy is this thing that's going to determine your actions given the current state that you're in. Well, today we're going to now expand that. I'm going to introduce the Markov decision process as a model to driving this reinforcement learning. I'm going to introduce this concept of episodes, that is, you start in one state and then the policy dictates that you do something and it gets you to new state, and then, the policy is going to drive you further and further and further, and you have this trajectory, this evolution from states that are ordered in time, if you will. And I'm going to introduce this dynamic programming, which is sort of like the foundation on which most of the the math that's underlying the reinforcement learning comes from. Next time, I'm gonna go into Monte Carlo and temporal difference learning, but we're gonna use it with artificial neural networks. Okay. Today we're just going to use, you'll see that it's just going to be like a tabular based method. Okay, so just a little recap again. Here's a link to the GitHub. You can find a textbook in the docs section. I'm pretty much all the way up to, today will be all the way up to like about chapter 4, getting into chapter 5. Basically all of the dynamic programming section. So from the beginning up to there is where we are. Okay, so I'll just recap. So remember, I said the bandits are presented at each step, and we came up. I introduced this little figure here, right? So the agent here is, well, the thing that has agency. It makes choices given what the environment is presenting to it. So the environment here is presenting to the agent a certain state. I'm in state 1, or I am a red bandit, or I am a green bandit. That's the current state. Given that state, the agent then makes a choice. The agent's following some kind of policy that tells it, if you're in this state, make this certain action. So it makes this action, and the environment will respond to that. The environment will then change its state as a result of it. In the case of this random bandits, it doesn't care what action you took. It's going to always just give you a random new state, a random new bandit. But imagine that if your actions had consequences that influence the new state, that's kind of what's happening here. And then there's also this other number, this reward, that tells you how good was that action, right? Like that you took. So then using those two new values, the new updated state and the reward you got for your previous action, the agent will make a new choice, what action to take in this context. And then it's you can see how it's kind of this iterative process, right? With events occurring in these discrete intervals. Okay, so what we have here is a Markov decision process, right? So like I said, the events are going to occur at discrete time steps, right? And let's, for today, imagine that the state space, the amount of states that you can be in, is finite. There's only so many. right? It isn't continuous space. And the actions too. So in that case, then you can write some kind of trajectory. Like if I started in state 0, I took action 0, I then got a reward, at the next step, that and the state updated. Given this reward and state, I took another action, and then that resulted in a new reward and new state. And I took another action after that, so on and so forth. And then maybe you have some terminating states. Who knows? This is not necessary, but you have what the point is, you have a trajectory that describes this evolution. And if I were to have enough trajectories, right, then I can describe some kind of dynamics with transition probabilities, right? Like when I was in state 0, I made a transition to state 1, with some kind of probability. You just count up the number of times you did it, right? So here's a little example. Imagine you have this little system here, this environment of 3 states, A, B, and C, okay? And let's imagine that there are 2 actions that can happen, right? There is a clockwise transition that transforms you from A to B or B to C or C to A, and a counterclockwise transition that goes in the opposite direction from C to B to B to A, right? Let's just say now that the counterclockwise transition, before I get into that, these states, let's imagine that they're sort of binary states, right? They have a value, 0 or 1, up or down. Maybe they're spin states in an Ising model, or true false conditions on some kind of logic tree or something, right? But they have these binary states, 0 and 1. And let's say that this counterclockwise transition is going to occur if I used X and Y to be the current in the next state, is going to, sorry, the current in the previous state. It occurs if the product of the current and previous state is 1, right? So like if I was in A and now I'm in B, then a counterclockwise transition will occur if 1 times 0 is 1, which is not true. So this counterclockwise transition doesn't occur. The clockwise transition is going to occur when you add those values of the current and previous state, mod 2, right? So if I add them, so if I'm in A and B, and if I add them, 0 plus 1 is 1, 1 mod 2 is 1, so it does happen. So I make a clockwise transition to C, okay? So if I follow these rules and I start off, my initial conditions are state 0 is A, and that should be a 1. State 1 is B, then I already told you the next one's going to be C, but what comes next? This is my question.
B.
Is what?
Would it be B?
Why?
Because C is 1 and then B is 1, so 1 times 1 is 1. So counterclockwise.
And the clockwise transition?
Is 0. So
yeah.
Well, actually, on the presentation, it doesn't say occurs if mod 2 x plus y is.
Oh, it's 1. Sorry, I got cut
It's
off.
1. Okay, yeah.
Yeah, like if it's true.
Okay.
So does it occur?
I don't think so.
Yeah, no. Yeah, 1 plus 1 mod 2 is 0, right? So yeah, it goes A, B, C, and then back to B, and then what? Anyone? So my current state is B and my previous state was C. What do you think is going to happen? What's the next state?
A.
Yeah, it's A. For the same reasons, right? It's a 1 plus 1, so it's a counterclockwise transition. So it goes to A. And then once we're in, so the next, I'll just go on forward. So if the next one, the current is A and the last one was B, then you're going to have a clockwise transition, right? Because 0 times 1 is 0, so that doesn't happen. And then 1 plus 0 is 1, so you get a clockwise transition. And then you're back to the beginning. So this is kind of oscillating. It goes A, B, C, C, B, A, B, C, C, B, A. And that's the trajectory. So if you were to write that all down, you can write a transition matrix, right? So you can write a transition matrix, right, that to describe the probabilities of being in state A, going to state A, being in state A, going to state B, being in C. So what value is in this element of the matrix? What's the A to A, the probability of the A to A transition? Okay, well, if you were to just look at the whole, if you were to write down the whole thing, like, this is just 0. Okay, what is the probability of A going to B? Recall that the pattern was A, B, C, B, A, B, C, B, A, B, C, B, A, B, C, B, A. Does everyone follow? Any questions so far? Huh?
I
Go
mean,
ahead.
like, it's just I don't want to be the only one who's answering, but
Yeah, that's, yeah. Anybody else other than John? No one? Okay, so I'm going to assume you don't understand what I'm talking about then. What don't you guys understand from like what I'm asking? Anyone? Don't be shy. Here, I'll call on someone. So Dada, what is the value that goes in here, the A B prime element?
1.
Yeah, why is that?
Because A is 0, so it has to be clockwise. Right?
Yeah, when you're in A, you always make a clockwise transition. A always goes to B. So the transition here, the A to B prime transition is always 1. And then I'll just keep you on the hook. What value goes in here then? What's the A to C? Well,
0.
yeah, it should be 0, right? I mean, like we just said, A always goes to B. So along this line, you can see how the sum of the probabilities must equal 1, right? So
Yes.
For the same logic, C always goes to B, right? Because it kind of makes this oscillating motion, right? A goes to B, B goes to C, C goes to B, right? So C always goes to B. So we know that C to B transition is 1 here and 0 everywhere else, right? And B can go to A or to C, right? With equal probabilities. So these are 1/2 each. Oops, can't draw. Okay, so what we've done is we just written a transition matrix, right? This transition matrix describes all the probabilities of starting in one state and ending in another. And if there was some reward assigned to it, I haven't talked about it, then it would this probability would give you that, right? So given your current state and the action that you took, what is the probability that you end up in state S prime and you get some sort of reward? And formally, it'll be written in this way. So what we have here is a model of the environment, okay? Defined by this transition matrix. Okay. So I need to erase now, right? That's how we do this. go to the mouse and then move up. All right. So now let's talk about those rewards, okay? So in that episode, right, we started in one state, took an action, and the consequences of that action yielded a return, a reward, right? And so along this episode, you can write down this list of rewards, and we can imagine that maybe we want to maximize rewards. I kind of already hinted at this before, right? We want to maximize rewards, and so the simplest way you can do this is just add up all the rewards that you get. So at a given time t, the value of it is going to be the sum of all the future rewards you will get, right? So if I'm in state if I'm at a particular state at time t, you could think of maybe the value of that state is going to be equal to the sum of all its future rewards, which of course you don't know yet, right? Last time we talked about it, the discounted sum of rewards, and that's just basically this gamma factor that discounts farther away in time rewards less and less and less, and you could just write it like this. But either way, you have this value g of t, which sort of quantifies a value assigned to a certain point in time. And so g of t is going to be finite if the rewards are bounded. Like these rewards have specific values, they don't blow up. You can never get a reward of infinity. And if, like I said before, if the reward space is finite, like you only have reward, you can get a positive reward of 1 or no reward, or just 0 or 1, or just a handful of rewards, and this all holds true. And of course, if that gamma term is a positive number between 0 and 1, right? Such that when you start taking, when you exponentiate it, the value gets smaller and smaller and smaller. So yeah, this number will be finite. I mean, this is just in practice. We usually give the terminating state, if there is one, a reward of 0. But the value function then, it tells us how good is it to be in a given state when we follow a particular policy. That's kind of like what we're doing here. Okay. So let's think about this value function, right? So we say this value function, v of pi, for a given state is going to be the value, it's going to be the expected sum of rewards, of future rewards, given that you're at this current state, right? And so we just substitute this, the formula for g of t that we had before. Here it's just a discounted sum of rewards. And it's written like this, right? And this expectation, pi, is going to be an expectation over, it's the average over trajectories that follow this policy. Does that make sense to everyone? Right, because this is kind of like the first building block here in this is reinforcement learning, how we assign a value to particular states. How good is it to be in a particular state? We also, in our current example, like the action doesn't matter, right? The state's going to do what it does. But if you had if the next state depended on what action you took, then what you have is an action value function, right? It's the same thing. It's a state plus action. What is the value of taking this action at this state, right? And so how do we do it? Like we just solve it from experience. It's an expectation. It's an average over trajectories that follow that policy. So you just have the agent follow the policy, and we're just going to tally all the resulting rewards and states. Now, if the state space is huge, then you're going to need a lot of trajectories just to sample the state space like appropriately. And so that can be prohibitively expensive. Also, even if you could just run it for like, a long enough time, you may run out of memory. You have to hold all these trajectories in memory. And so in practice, doing it like this isn't really useful, right? So this is where Bellman comes in the Bellman backup, right? So we find that this value function is going to satisfy this recursive relationship so we wrote that it's an expectation of the sum of future rewards. And well, we know that the sum of future rewards is going to be just the immediate reward at the next time step plus the sum of future rewards, from there on after, right? Like we did in last week. And so you can see here to solve this this bit here, the current reward, you're going to you start from a current state, and then you consider all of the possible actions, and the states that they would end up in, right? So you sum them all up times the probability of making that transition, the probability of making the transition from S to S prime, given a certain action. And that's defined here, right? What is the probability of ending up in state S prime with a given reward, starting from state S, given a certain action, right? So this is the probability. This is defined in that transition matrix, right? We're going to sum over all the actions, weight them by the probability that you took that action given that state. For now, let's just say that this is let's just say this is 1 for right now. And then you sum over all the future states and rewards, right? So that's it's just taking an expectation, right? The sum over all the possibilities times the probability of making those transitions. And that's going to give you R. And then this last bit here, well, that's just going to be this recursive, right? This is the expectation starting in the new state, right? S prime, and then whatever the future rewards for that is going to be. So you can V, the value at state S is updated using the transition probabilities and then the values of those states, of those new states, using your same model. So this is known as the Bellman backup. Okay, does that make sense? It's essentially a bootstrapping method, right? You're using itself here to define the future values, which are needed for this part of the equation. This part you could solve analytically. We just did. It's an it's just an expectation. And this, you just plug itself back in. Okay. So what does this do? This means that we don't have to keep in memory all of the states trajectories, right? You just use the current state, evolve it to the next state, and then use its own function given the new state to update the value. And then you just move on. So it's kind of like that running average idea we introduced last week. Okay. Okay, so now I can talk about dynamic programming. Okay. So in dynamic programming, what we want to do is figure out a way to find that good policy, right? So far, I've just said that we have a policy, but maybe we want a systematic way to improve our current estimates of a policy. So to do that, we need to have a model of the environment, right? You can see how already this is not going to be really useful, because often the environment is a black box. We don't know how it works. But in this case, it's an ideal situation. We know how the environment works. Maybe we have some transition matrix like before, something like that, right? Or we know the physics behind it. The state space also has to be finite, okay? We can't have a continuous state space. Sometimes you can get so in some instances you can approximate this by binning the continuous state space and then to have a discrete, discrete states. And yeah, and so we're going to use the Bellman equation to govern how we update the approximations. So for the value function V star, this is going to be like some optimal value function. You're going to use this bootstrapping, right? Like that we described before, sum over all future states. So you're in a current state, sum over all future states times the probability of making that transition. Use the value function on that new state, but we're gonna use the max action, right? We're gonna use the action that maximizes this value. In other words, take the best action, right? So you're in state A, given all the actions, take the best one, and use that action here to define the probability, and then plug in. Use this bootstrapping to plug in the value function for the next state, and that's how you update the value function. For the action value function, it's the same thing, only that we're going to be maximizing on the future action. That is the action that you take at the next state. Okay. So this is basically the essence of dynamic programming. Okay, and so to implement this, it's pretty simple. You can do it iteratively, right? So we say that the value function at some step k+1 is going to be that equation we wrote earlier. So we're going to sum over all the actions and all the future states times the probability of making the transition, and you bootstrap, more bootstrapping. But here we're doing the, your current estimate of the value function. So the new value function is going to be some function of your current estimate. So this is how you update the value function. So how do you do it? So usually we start with this value function. Remember, the state space is finite, so you could kind of think of this like a vector with state 1, state 2, all the possible states, state A, B, C. You assign them all to be 0, right? They'll have 0. And we're going to have some threshold parameter here I'll talk about in a second. So we initialize all the states to some value. Usually it's 0. If there's a terminal state, the value must be 0 because you don't get returns on a terminal state. And you're just going to loop forever. Okay, so so for each state in the state space, we're going to calculate this v, the value. So you take your current value function for that state and save that. Okay, and now we're going to update the value function, right, using the equation we had before, and you're going to use the it's for this Bellman backup part here, this bootstrapping. You're going to use your current estimate of the value function on the new state. Plug it into here to give you the new estimate. And now you compare. You say that value, this is a vector, right? Remember the difference between my old estimate and my new estimate. Give me the distance between them, right? And if that is smaller than some threshold, then we're done, right? So just do this until these point in the same direction. Does that make sense? So we're just going to keep looping. We just keep loop. We loop. We have to actually sweep over all the states before we want to, it's 2 nested loops before we make another big loop. Okay, so you sweep over all the states, update your estimate of the value function, and compare them. Has it changed? Have we converged? And if so, then we break out of the loop. Okay, so it's that simple. So this is how we do policy evaluation. We can show that this V of k is going to converge onto some finite value. Right? So this is how we iteratively solve for the value of each state, how we assign a value to each state in this system. Okay. Any questions so far? This is kind of like a heady topic right here. So my idea is that to have you guys sort of implement this to do policy evaluation. But I think most of you guys can follow the pseudocode quite well. So let's move on. So we know how to evaluate, how to assign a value to each state given a certain policy, but how do we evaluate the policy itself? Like, is there a better policy? You know, and so to do that, to probe that, you can ask, say, I'm in a current state, and the current policy I have says I should take action A. But what if I did a different action, right? What if I took an action that's off policy, right? Well, if we have some value function, action value function that assigns the value to a state given a certain action. So here, this is the action determined by some other policy, pi prime, right? This is a different policy. Given that state, it says do some different action, right? If the value of that is bigger than the value I get for the state following the current policy, then this new policy must be better. In other words, this is saying I have a current policy, and when I get to this point, this policy is telling me to go in this direction, take this action, and steer the trajectory in this direction. Doing that will result in all these trajectories, and if I did my the iterative value function approximation I showed in the last screen, if I did this, I'm going to get an answer. I'm going to get an answer. It's going to give me a value to that state, right? What if at that one point, at that state, I followed a different policy, and it generated a new set of trajectories, and I evaluated them, iteratively like this. Again, I'm going to get different values, right? I'm going to get different values, and that's what this is implying. And if these values are bigger than these values, then surely this policy is better because it results in bigger sum of future rewards, right? So you can go through it in the book on the proof here in this like rarefied case, but you could show that if the value you get following the new policy is bigger for all states, is bigger than the value of the current policy given that state, then the value of this new policy is bigger than the value of the old policy. So now we have a way to probing whether one value is better than another, right? So how would we try to implement that, right? So this is known as policy improvement. Okay, so here's an example straight out of the book, right? So this is their grid world, right? These little boxes, those are the states. These grayed out squares, these are terminal states. So the value for them is by definition 0, right? And initially, we're going to have a random policy, right? And we're going to assign a value to each one of these states. We're going to initialize them all to 0. Each state has a value of 0. We don't know how good any of them are, right? And the policy is completely random. At any given place, there's equal probability of going up, down, left, or right, right? This is where we start. So we have a policy and we have values, right? So following, so this is their initial values for the states. If we were to follow this just random policy, then if I were to solve it, you know how he said like follow trajectories following that policy, and calculate those averages to get the value approximation. This is the value you'd get, right? So if you're in this state, oh, I'm sorry, I should say that transitions have a value of -1. So every time you move, you make the value assigned to it is -1, right? If you're in this state, it's terminal, so you get 0. But in this one, you could have made any transition, right? They're all equally probable, right? And so you get, on average, the value is -1, right? So if I use these values then to determine the optimal action I should take at that state, then you can see how here, this is the state with the highest value, isn't it, right? Because these all have a value of -1. So my no longer is the optimal action, no longer are all actions equally good. Clearly, making the transition from here to here is better. So this policy has been updated, right? So for state here and here, the best place to move is here to this terminal state. For all these other ones, it's equally likely. I mean, there's no one state is better than the other. Okay, so now if you use this policy and calculate the values for it, you'll get, so you generate trajectories, right? Using that policy, and you'll get this value, these values, right? There's updated now a little bit. You can see that at this state here, -1.7 is bigger than -2. So from here, you should go up or to the left. And that's what this is saying. And the states along this diagonal, you know, they all have the same value of -2. So, you know, all actions are equally likely. So you see how you can iterate, right? You solve for the values given your current policy. We initiate with 0, generate trajectories with that policy, and then calculate the new values following that policy. Those values then will determine what the best strategy should be, right? What the best action should be. This determines your new policy. This policy generates new trajectories, which update the values. You do this over and over and over and over, and you'll see that your policy is improving. These values will converge for these kind of finite systems. And here they show the value here at k equals infinity. But notice that after like k equals 3, despite that the values are improving to the more, you know, are improving, the policy is not changing anymore. Okay. So, you know, mathematically, you could just write it like this then. You can say that the value following that new policy for the state is going to be, like I said, following that the action that maximizes this expected sum of returns, which is you know, encapsulated in these numbers here, right? So that's how we improve the policy, this sort of iterative fashion, right? Sorry, this two-step process: value estimation and then policy improvement. So this is how you do it. So just like we said, you initialize your value function to be zeros everywhere, right? For all states. And then we're going to evaluate the policy, right? Just like we did before, right? So you loop over loop over all the trajectories, right? Sweep over all the states and update your value estimates, right? Do this until you've converged, right? Till your values don't change anymore. And then use those new values to dictate what the policy is. So we're gonna say the policy is stable. I'll show in a second what that means, right? So we initialize with the policy stable is true, and then we're gonna sweep over all the states, okay? So our current policy at that given state is gonna determine what action I should take following that policy. But instead, we're gonna update the policy. We're gonna say argmax, the action that maximizes that return. That's the action you should take. So we update the policy. They say the policy for this state is now going to be this maximum action, this action that maximizes this, not the old action. And now you compare. Is the old action equal to the new action, right? If they are not equal, then the policy is not stable, right? It means you should change the policy. If it's telling you that the new action is equal to the old action, it means that your policy has converged. And so your policy is stable, right? So you loop over every state and it's gonna tell you if the policy at each one of these states is stable or not, okay? And so if it's stable, then stop. For all the states, the policy isn't changing anymore, you can stop. If not, then you need to go back to 2. You've updated your policy, it's not stable, but use this new policy to do policy evaluation. This is going to give you new V's. And then you use those V's to determine what the new policy is. And if if the new policy says that the actions are all the same, they're not changing anymore, then you can quit. So that's how you do policy iteration. Okay, any questions so far? Okay, we have about 10, 15 minutes left, so I should hurry up a bit. All right. So recall that the policy, it didn't change after k equals 3, right? I could just go back. The policy isn't changing anymore. So was it necessary for me to converge this value to iterate this all the way up to convergence? I don't think so. You just needed to do it up to a certain point, right? Well, what if we took some extreme limit? What if we sort of merged the two concepts? What if I just did one update of the value approximation and then use that to update the policy, you know? So that's what this method, this implementation gets at. So it's an approximate method. We're not going to converge all the way. We're just going to take one step, and you'll get star means optimal, right? You're going to get a policy that's close to the optimal one. It's an approximation. But what's better is that we've eliminated this step here. Step 2 says to converge. It says to loop over all the states until your value function has converged. We're only going to do one step, and we're going to merge these two concepts where we're going to update this value function given the action that maximizes the future sum of rewards, and that's written right here. So I'll walk you through it. So in the algorithm, we still have some threshold that tells us whether the value function is changing anymore. We initialize everything, so we'll just say everything is 0, right? And we loop over all the trajectories, right? So we generate a new trajectory. So for each state, then, we're going to save the value function for that state, and we're going to update the value function here. We're going to update it using the transition matrix that we had before, the old estimate of the value function, and we're going to choose the action that maximizes this value here, just like we did here. right? So we're sort of merging the two concepts. And we use that to update the value function. Check if the value function has changed, and if not, then you can exit the loop. But if you haven't, you generate a new trajectory and you do this over and over and over again. Notice this is only one loop. So this is, well, there's two loops, so you have to loop over trajectories. But we've eliminated this costly step. So this is way more, way faster than the the actual method, right? And this is an approximation. So, and what we're going to get here then is we're going to get a policy that's close to the optimal one. And I think, so yeah. And so what I've got for you today then is now a method to find the best policy, or at least how to improve your current policy. Okay. And the caveats are that you're going to need a model of the environment, right? That transition matrix. And the state space needs to be finite. So this algorithm or this dynamic programming only works in a very limited set of problems. Usually the state space is not finite, right? We have continuously varying features, and we want to know what to do, what action to take during, given some continuous set of features describing the state. And yeah, what to do when when we don't know under the hood, we don't know what the environment, how it behaves. And that's exactly what we're going to do next time. It's going to be model-free learning with Monte Carlo and then temporal difference learning. And we're going to treat continuous states with neural networks, right? So in the neural network, you have a set of features that go in, they could be continuous, and output comes, what action to take, right? So combining those two, you can now do, the set of problems that are, that matter, right? The set of problems that we run into all the time. All right. Yeah, 7 minutes under. Okay, so does anybody have any questions so far?
I mean, personally, the math part, the formula part, was a little dense for me. But I think if I look over it one more time, it should be clearer.
Yeah. Just go up to the chapters up to dynamic programming, and it should, yeah, be a little clearer. So what I've hopefully have given you here is a sort of big picture of what we're doing, right? Where we have formalized sort of how to calculate rewards or future rewards, and sort of said to ourselves, what we want to do is maximize rewards. I've given you ways to calculate the values of states given your definition of future rewards, right? So now we know how good is it to be in a current state. And all of this came out of the space, came out of the world of models where they had finite space, like grid worlds and stuff like that, or that ABC state that I had before, which is all fine and good to formalize the math, but they don't really translate to real world problems. And we're going to use these concepts, this Bellman backup and whatnot, next week. So with that, if you have no other questions, then yeah, I'll just leave it there.
Sounds good.
Yeah.
Thanks.
All right, guys. I'll see you next week.
Thank you.
Yeah.